topic of today's video is again Frobenius series solution, and in this video we will discuss the case that while solving a second order differential equation using Frobenius series method, one of the coefficient of y becomes infinite. Right? This is very similar to the case as we discussed in our last video, case 3, where one of the coefficients of y becomes indeterminate. Right? And this that kind of situation happens at the root which is the smallest root of indicial equation. Right? So I will call it case number 4. However, we will see that this is the most general case when the roots are distinct and they differ by an integer. I will tell that later. So to start with, we can write if the roots of indicial equation r1 and r2, they are not equal, right, and they differ by an integer. This is r1 minus r2 is equal to an integer, right, and we suppose that r1 is greater than r2, right, then and n becomes infinite at the smallest root r2, r equal to r2, right. So we will see that this kind of situation, that one of the coefficient becomes infinity, happens at the smallest root always, right. Then the solution is given by y equal to c1 y1 plus c2 y2, where y1 is the first solution which is obtained by plugging r equal to r1 in your Frobenius series, right. R1 is the biggest root, and the second solution is obtained by differentiating y star partially with respect to r and then evaluating it at the smallest root, where I should mention that what is y star? Y star is actually r minus r2 multiplied with y, right. So this is an important point, how to obtain the second solution. The first solution is obtained by just plugging the biggest root in our solution y, but the second solution is obtained by this formula, right. First you have to obtain y star, that is just the product of solution y with r minus r2. Note that r2 is the smallest root, the point of misfortune, right. Misfortune in the sense that the situation of the coefficient becomes infinity happens at the smallest root always. That's why we are calling it a point of misfortune, right. And then after finding y star, we will differentiate with respect to r and then plug r equal to r2. That will be our second solution, and then the linear combination will be the complete solution, right. So I will take the smallest simplest example to understand this concept. So example number 1, the simplest differential equation we can take is x y double dash plus y equal to 0, right. And since nothing is stated in the question, so it is automatic that the solution should be obtained around the point x equal to 0, right. So we can see that the coefficients are px. The px is actually the coefficient of y dash in the standard form. The coefficient of y dash is absent here, so px will be equal to 0, and qx will be equal to 1 over x. You can see that px, that is a constant, it is an analytic function, but this is not analytic at x equal to 0, right. So I am writing for this qx only is not analytic at x equal to 0. However, this is analytic, right, at x equal to 0. But if you multiply your px with x, that becomes 0, and you multiply qx with x square, that becomes x, then they both become analytic. This is a constant function, it is always analytic. This is a polynomial, it is also analytic. They both are analytic at x equal to 0. So we can say that x equal to 0 is a regular singular point, right. And when we say that x equal to 0 is a regular singular point, we hope that the solution for this differential equation is of the Frobenius series form, right? So suppose the solution is y is equal to summation n equal to 0 to infinity an x to the power n plus r. This is the solution. That is called the Frobenius series, right? You can write it in expanded version also. I will write that here, equal to x to the power r a naught plus a1x plus a2x square and so on. And note that this a naught should not be equal to 0, right? Now I will differentiate it twice and I will plug those values here. So obtaining its derivative, y dash and then y double dash, I am writing it directly, right? So differentiating it twice will give you n equal to 0 to infinity n plus r n plus r minus 1 x to the power n plus r minus 2, right? So I have skipped the evaluation of first derivative. I have written the second derivative directly, right? And note that on differentiating a Frobenius series any number of times, the range of the summation becomes unaltered, right? It does not change. While in case of power series, on differentiating a power series, the range gets changed, right? So there is a small difference between the two series, right? Now I will plug those values here in my differential equation. So this gives x multiplied by with y double dash, so that will produce summation n equal to 0 to infinity an n plus r minus 1 x to the power n plus r minus 1, right? And then plus y summation an x to the power n plus r equal to 0, n equal to 0 to infinity, right? So this is the relation, and from here I should compare the least powers of x in order to get the indicial equation, right? Note that if you want to obtain an indicial equation, you have to compare only the least powers of x, right? Comparing any other power of x will not give you the indicial equation. So be careful at this point. The least power of x that can be obtained from these two summations is x to the power r minus 1. You can see that you put n equal to 0 here, you will obtain x to the power r minus 1. But from here you are getting x to the power r. So out of these two summation, only x to the power r minus 1 is the least power term. So I will equate that term, equate coefficient of least power of x, that is x to the power r minus 1 in this case. And from the first term, you can get x to the power r minus 1 by just plugging n equal to 0. So that will give you a naught times r into r minus 1. But from here you are not obtaining any term containing x to the power r minus 1. So only one term will be there, right? And from here you can say that r times r minus 1 equal to 0. As you already know that a naught can never be equal to 0 from here, right? Okay. So that will give you two roots, r equal to 1 and then r equal to 0. So I will call it r1 and this will be my r2. Note that I have assumed that my r1 should be greater than r2, right? So you have to follow this in order to use this solution, right? So always take the biggest root as r1, right? So now comes the decisive step. You can see that the roots are distinct and they differ by an integer, right? Note r1 is not equal to r2. First thing is that, and their difference is an integer value, right? So at this point you have to decide that whether you will follow case 1, no, case 2 or case 3, sorry, case 3 or case 4. Case 3 was when we got distinct roots and they differ by an integer, right? And case 4 is also same, but the difference is here, the behavior of coefficient, right? In case 3, one of the coefficient becomes indeterminate, while in case 4, one of the coefficient becomes infinite. But at this point, you don't know whether you will follow case 3 or case 4. I have to identify one or more coefficient, maybe A2, A3, A4, and we'll see that coefficient becomes indeterminate or infinite, right? We'll have to wait for that. Do not take any decision at this point, right? But we still know that either case 3 will follow or case 4 will follow, because case 1 was when we got distinct roots but they were differing by a non-integer value, so that was our case 1, and case 2 was when roots were repeated, right? So there are two possibilities after this point, case 3 or case 4, right? Now what I will do, I will compare the highest visible powers of x, and if you see these two summation, the highest visible power in summation is x to the power n plus r, and we'll find that whether one of the coefficient is becoming infinite or indeterminate, right? So equate coefficients of x to the power n plus r, right? Okay, so from the first term you can obtain x to the power n plus r by putting n equal to n plus 1, so that will produce a n plus 1, n plus 1 plus r, and n plus 1, so that will give you n plus r, right? Okay. And from here the coefficient of x to the power n plus r is a n itself is equal to 0, right? So you can see that you have to obtain the value of the biggest subscript coefficient in terms of the least subscript coefficient. So a n plus 1 should be obtained in terms of a n, so that will produce minus of a n divided by n plus 1 plus r and n plus r, right? This is your recurrence relation, and using this recurrence relation you have to see that what happens for a1, a2, a3 and a4, so on, right? So I will start with n equal to 0. If I put n equal to 0, I will get a1 equal to minus of a naught over, putting n equal to 0 will produce r plus 1 times r, right? Now this is a decisive step, because I have to still make a decision that whether I should follow case 3 or case 4. At this point you can see that if you plug r equal to 1 here, right, then a1 will be minus a naught by 2, I think, right? And but if you put r equal to 0 here, the smallest root, right, as I said earlier that if something misfortune happens, that happens at the smallest root. So if you put r equal to 0 here, the denominator goes to 0, and then minus a naught upon 0, that becomes infinity, right? Because a naught is not equal to 0. So something non-zero divided by 0 will give you infinite, and at this point you can decide that you have to follow this case 4, right? So I will write that first. This is my a1, right, and it may take two values for two cases of r. First is r equal to 1, and then second is r equal to 0. This is just a decisive step. However, this is not needed in our calculations, but to make any decision we have to write this, right? So if you put r equal to 1 here, you will get minus a naught upon 2. But if you put r equal to 0 here, you will get minus a naught over 0, that will become infinity. And at this point you can decide that we have to follow case 4, right? Okay. So for case 4 I have to find the next coefficients. If n equal to 1, from here I will get a2 equal to minus a1 divided by r plus 2 and r plus 1, right? But a1 is already obtained, so I will plug this value here. That will give me a naught over r plus 2 r plus 1 whole square multiplied with r, right? So this is a1, this is a2, fine. And yeah, we will use these coefficients. I am not finding the higher coefficient. I have already three coefficients, a naught, a1 and a2, right? That's fine. Okay, and note that you actually need not to evaluate the value of a2 at these points, right? You just leave it in terms of r, right? Okay, now I will plug those values here in my solution. Where is that? This y, right? I will call it equation number 1. Equation 1 becomes y equal to x to the power r, and a naught will be taken common, and 1, then a1x. But what is a1? A1 is this much, so it will become minus x divided by r plus 1 times r. Another term will be x square over r plus 2 r plus 1 whole square times r, and so on, right? So this is your y in terms of r, right? From here you will obtain your first solution y1, and that can be obtained by directly putting this biggest root here, right? That will be a y1. So I will find that. So first solution will be y1, and that is obtained by plugging the biggest root, that is 1 here, right? So that will give you a naught x 1 minus x over, I think, 2 factorial plus x square over 3 to 1, that will be 3 factorial, and then multiplied with the 2 square, right? 2 square, and so on. So this is your first solution, right? Now what is left? That is our second solution. But in order to obtain second solution, you have to do some modification. This we cannot carry with this y, right? Because in order to obtain second solution, we have to finally put r equal to 0. But putting r equal to 0 is producing infinity. If you put r equal to 0 here, you see that you will get infinity, right? So that is surely not working this time. For second solution, we have to do some modification, and in order to do that modification, we should first find this y star, right? Okay. So second solution will be obtained by y2 is equal to del y star over del r, and then we'll put r equal to r2, and we have to mention that what is y star? Y star is r minus r2. You can see that your r2 is 0, right? And multiply with this y in terms of r, right? So I will evaluate this first. That is, y star will become, if you multiply your y with r, that will become a naught x to the power r minus x, and if you multiply all of these terms by r, you can see that from the denominator that r will be cancelled, right? And that is the purpose why we multiply this by r, right? In order to get rid of this r in the denominator. So this will be your y star, right? I will call it improved solution, right? And then you should differentiate it with respect to r. You can see that del y star over del r, and that is again an important point. Then del y star over del r, right? Be careful at this point. You are going to differentiate with respect to r partially, but you have to use product rule, right? Because r is present here, and a naught will be treated as a constant. So what I will do, I will use product rule. First, I will differentiate the first function. That will give you x to the power r log x, yeah, okay, right. And second function will remain as it is, minus dash, and then the first solution as it is. Should I write a naught? Okay, fine, a naught x to the power r, and differentiating it with respect to r. This is a very important point, because there are several terms containing r or factors of r plus 1, r plus 2 in the denominator, right? So differentiating will be difficult. You have to use some special formula in order to differentiate these terms like this, right? So this is easy. Differentiation of the first term will be 1, that is easy, but differentiation of this will be, if you want to differentiate it using that product rule or quotient rule, you will get plus x over r plus 1 whole square, right? That's fine, but differentiating this will cause you trouble, I think. Yeah, so you have to use a method where we find the derivative of a function which is present in rational form, px divided by qx, and px is present in factors and qx is also present in factors. If you remember that, you have to take log on both sides, right? I will write that method here. Here hash, if you have something like this, if you want to differentiate this d by y is equal to, suppose you have y is equal to x minus a over x minus b, and you have x minus c square here, suppose you have this, right? And you want to differentiate it, right? So in order to obtain, find y dash, right? So you want to obtain its derivative, and so what you do, you take log on both sides, right? Then you will get log x minus a minus log x minus b minus twice of log x minus c, right? And when you differentiate this, you will get 1 over y dy by dx, right? And 1 over x minus a minus 1 over x minus b and minus 2 over x minus c, right. And after this you take this y here on multiplication, so I can erase this. So y dash equal to y multiplied with this whole thing, right, and y is this value, right. So this is a kind of method you can use to find the derivative of a rational function px over qx when both px and qx are present in factorized form, linear factors, right. So I'm going to use this concept here, right. Okay, right. So now you can see this term. This term is of this nature. However, no factor of r is present in the numerator, so that is good. Okay. So according to this formula, the derivative of this function with respect to r will be like this: y, the whole function. Okay, whole function is x square over r plus 2, r plus 1 whole square. However, I should write that x square hereafter. Okay. X square, right. Okay, so this whole function is here, and then 1 over x minus a. You can see that this x minus a was present in the numerator, that's why 1 over x minus a, right, and negative sign before those factors which were in the denominator. So we don't have actually any factor in the numerator, so there will be no term. Only two factors are present in the denominator, so I will be starting with the minus sign, minus 1 over r plus 2 and minus this 2 over r plus 1, that's it, right. So this is a kind of shortcut trick in order to obtain the differentiation of such kind of functions, right. So I will put a hash here, and the explanation of this hash is this, right. Okay, x square and minus dash dash dash, so on, right. So this is my del y star over del r. Now I will plug r equal to r2 in order to find y2, right. So therefore y2 equal to del y star over del r and r equal to the smallest root. If you put r equal to 0 there, you will get a naught. I think a naught should be taken common, right. And yeah, log x, and then 0 will give you minus x over 1 plus x square over, putting r equal to 0 will give you 2 dot 1 square, 2 dot 1 square minus so on, right. And then plus a naught was taken common, x to the power 0, that is 1, and 1 plus x over 1 square, and then if you put r equal to 0 there, you get 2 into 1 square, right. So 1 over 2 dot 1 square and minus 1 by 2 and minus 2, that will be minus 5 by 2, minus 5 by 2. So ultimately that will become minus 5 by 2 square, right. So minus 5 x square by 2 square dot 1 square, right, and so on. Okay, right. 2, right. Now you can see that this is the second solution, and you already have your first solution. The complete solution, y is equal to c1 y1 plus c2 y2 is solution, right. You can use those values of y1 and y2 and plug here, you will get the complete solution. I am not writing that, right. So this is how Frobenius series solution works in the case when one of the coefficient becomes infinite, right. I will take one more example for this, and this time I will change the coefficient. Example number 2, solve x y double dash plus 2x y dash plus 6 times e to the power x y equal to 0, right. And this time you can see that we have this special kind of function present here, 6 e to the power x exponential function, for which you have to use a series of exponential function, because comparing powers of x will be difficult this time due to the presence of this function, right. Okay, solution. So you can see that your px is actually 2 and your qx is actually 6 e to the power x upon x. You can see that this is analytic, but this is not analytic at x equal to 0. You are getting infinity is not analytic at x equal to 0, right. But if you multiply your px with x, you will get 2x, and if you multiply your qx with x squared, you will get 6 times x e to the power x. They both become analytic, right? There's no problem with x equal to 0. If you put x equal to 0, they are equal to 0, 0, and both are analytic, right? Are analytic at x equal to 0. So we can say that x is equal to 0 is a regular singular point, right? So when we say that x equal to 0 is a regular singular point, we should hope that our solution should be of the Frobenius series, and that is summation n equal to 0 to infinity x to the power a n x to the power n plus r, and in the expanded version it is x to the power r a naught plus a1x dash s dash, and we should remember that this a naught is not equal to 0, right? So I will differentiate it twice and I will plug those values here. So that will be y dash equal to summation n equal to 0 to infinity a n n plus r x to the power n plus r minus 1, and its double derivative will be summation n equal to 0 to infinity a n n plus r n plus r minus 1 x to the power n plus r minus 2, right? So putting these derivatives here in this equation, right? But I will rub that first because I need to expand this e to the power x also, right? So plugging these values here in my differential equation will give x multiplied with y double dash, that will produce summation n equal to 0 to infinity a n n plus r n plus r minus 1 x to the power n plus r minus 1, right? And 2 times x multiplied with y dash, that will produce a n n plus r x to the power n plus r, right? And now the third term, right? Be careful at this point. You have 6 here and you have exponential function here, so you should use its expansion. E to the power x is 1 plus x square by 2 factorial and so on, right? You just need 2 or 3 terms, and then the value of y, that is this value summation n equal to 0 to infinity a n x to the power n plus r equal to 0, right? So you have 2 series here. One is this exponential series and this is Frobenius series, right? So be careful at this point. You have to multiply these 2 series in order to get the powers of x, right? So first what I will do, I will equate the least powers of x, and this is very important point. If you see that you put n equal to 0 in the first summation, you are getting x to the power r minus 1, right? From here you are getting x to the power r. So out of these 2 summation, the least power of x is x to the power r minus 1. That is clear. But here finding least power of x is not easy. First you have to, I think you have to write this series in expanded form. So what I will do, I will write this series in expanded form rather, and writing that using this, that will give me a naught x to the power r plus a1 x to the power r plus 1 and so on, right? So this is a kind of different point. So far we have been using this summation form, but in this example, due to the presence of this exponential function, right, or non-polynomial function, I have to use this expanded version, right, in order to compare the least powers of x. Now again, and from here you should also check what is the least power of x. From this term you are getting x to the power r minus 1. From here you are getting x to the power r, right? But from here, what is the least power term? If you multiply these first 2 terms, that will give you x to the power r, right? And if you multiply the next terms, you will get the higher powers of x. Means every term will contain x to the power r plus 1, x to the power r plus 2 and so on. So the least power from here will be x to the power r. First thing is that, right? So out of these 3 terms, the least qualifying power of x is x to the power r minus 1, right? So what I will do, I will equate that power, least power, because you have to equate only the least power in order to get an indicial equation, right? Comparing any other power of x will not give you indicial equation. So be careful at this point, especially for this third term, right? So equate least power of r, that is x to the power r minus 1, right? And from here that is a naught r minus 1. From here you are not going to obtain any powers of x to the power r minus 1. From here also the least power of x is x to the power r, so from here there is no contribution, equal to 0, right? And from here you can find r equal to 1 and r2 equal to 0. As you know that this a naught is not equal to 0, right? Again you can see that the difference is an integer and they both are distinct roots, as r1 is not equal to r2 and their difference is an integer, right? So at this point we hope that either there will be case 3 or case 4, right? Do not overjudge the problem at this point. You have to find some coefficient, right? Okay, now I'll find one more important point. Now in most of the cases you are able to equate the highest visible powers of x, that is generally x to the power n plus r, and you obtain a recurrence relation. But in this question you cannot obtain a recurrence relation because that is difficult this time. If you see this equation, right, you can see that the highest visible power is x to the power n plus r, yeah, right? But from here actually it's an infinite series, right? First thing is that and in order to obtain the coefficient of x to the power n plus r, you have to do several multiplications, right? You can see that if you want to obtain x to the power r plus 2, suppose r plus 2, x to the power r plus 2, then you have to do 3 multiplication. First the multiplication of this 1 with the third term, I will write that a2 x to the power r plus 2, right? You have to do 1 multiplication, 1 multiplied with this thing, then you will get x to the power r plus 2. You have to multiply this second term with this term in order to get x to the power r plus 2, right? You have to multiply this third term with this first term in order to get x to the power r plus 2. So you can see that in order to obtain x to the power r plus 2, you have to do 3 multiplications and then coefficient becomes big, right? And you want to obtain the coefficient of x to the power n plus r, as you have been doing in last questions, right? So the calculation will be very complicated. You have to do several multiplications here, right? So that is not a wise decision to search for a recurrence relation, right? So do not search for a recurrence relation at this point. In this kind of example, you should just proceed with the next highest power. So what is the least next powers of x? The least powers was x to the power r minus 1. The next power will be x to the power r. The next power will be x to the power r plus 1. So you have to follow like this. You have to go like this, right? Do not search for the recurrence relation, right? Okay. So what I will do, I will just equate the next power. Equate powers, sorry, not powers, coefficients of x to the power r, right? So from here you can obtain x to the power r by putting n equal to 1. So that will give you a1 r plus 1 r. From here you can obtain x to the power r by putting n equal to 0. So that will produce 2 times a naught r, right? And be careful at this point. You wish to obtain the coefficient of x to the power r, and you can see that if you multiply these first terms, you are getting x to the power r, right? And further multiplying any 2 terms, you are not getting any x to the power r term, right? You can see that you multiply this x with this thing, you are getting the higher powers, right? So only 1 multiplication is needed at this point, right? So the term is plus 6 times a naught. You can see that multiplication of this will produce a naught x to the power r, and then you have to multiply it with 6. So this will be the term equal to 0, right? And we'll see that if we equate the further powers of x to the power r plus 1, this term will become big and big, right? So from here I can obtain a1 in terms of a naught, so that if that goes on the left hand side, that will be minus 2 common, and I think r plus 3 and a naught divided by r plus 1 and r, right? So at this point you should again do some inspection at these points, right? What happened, whether the coefficient is become infinity or indeterminate, right? If you put your biggest root r equal to 1 here, you will get 2 1 2 2 will be cancelled, 4 minus 4 times of a naught. If you put r1 equal to 1, right? But what happens if you put your small root, that is r2 equal to 0 here, right? You put r equal to 0, the denominator goes to 0 and the coefficients become infinite. So at this point you can decide that you have to follow case number 4, right? Okay. Now what I will do, I will try to find the coefficient a2. One more coefficient is needed. Actually 2 or 3 terms are needed in order to see a solution in good form, right? So I have to equate the next powers coefficient of x to the power r plus 1, right? So x to the power r plus 1 will be obtained from here if you put n equal to 0. Am I right? Yeah. So that will give you x to the power r plus 1. No, you have to put n equal to 2, right? That will give you a2 r plus 2 r plus 1. From here you want to obtain x to the power r plus 1, you have to put n equal to 1. So that will give you twice a1 r plus 1, right? And now again the important point, you want to obtain x to the power r plus 1, right? You have to do 2 multiplications this time. First multiplication is, if you should multiply this 1 with this term in order to get x to the power r plus 1. And the second multiplication is also possible if you multiply these 2 terms, right? Right. So 2 multiplications will give you the required coefficient, right? So plus 6 times, the first multiplication was 1 with this thing, that is 6a1, and the second was x with a0. Okay, a0 equal to 0. So you can see that while comparing the lower powers of x, we get only 1 term, but as we move on equating the higher powers of x, this coefficient gets bigger and bigger, right? So this is an important point and dangerous point. Do not try to compare the visible highest powers of x, that is x to the power n plus r, right? Okay, from here I will try to obtain a2, right? So a2 will be, this will go on the right hand side and that will become minus 2a1 r plus 1, and that will be right, r plus 2. This is the first term. Then minus 2a1, I think this will become minus 2a1 and minus 6a1, that will become minus 8a1, right? So minus 8a1 divided by r plus 2 r plus 1, right? And yeah, or should I write these 2 terms as a 1 term? Okay, fine. Minus 6a0 divided by r plus 2 r plus 1, right? So if I take the LCM of these 2 terms, I think that will become r plus 2 and r plus 1, right? And here we are, r plus 1 should be multiplied with this thing, so minus 2 r plus 1, and here minus 8 times nothing. Okay, and I should take minus outside, a1, right? Minus common and 2 outside, or should I? Okay, fine, that's fine. Should I take 2 outside also? So if you take 2 outside, you are getting 2 here, 4 here, and then was r plus 5. Okay, so on simplification you are getting r plus 5 in the numerator. Okay, now this is your a2, right? And in terms of a1, and a1 is already known, this is your a1, so you should use this value here, and that will produce plus 2 square, is 2 square, r plus 5 is already here, and using a1 that will produce r plus 3, and divided by r plus 1 is here, r plus 2, r plus 1 whole square, and r, right? So 3 coefficients are sufficient. We have a0, we have a1, and we have a2, right? So now I will plug these values in y. So this is my equation number 1, this is my equation number 1, right? Equation 1 gives you y is equal to, a0 will be taken common, and x to the power r is there. Okay, x to the power r, a1 is 1. Okay, first term will be 1, then a1, this is a1, minus 2 times r plus 3 over r plus 1 r x, and another term is plus 2 square r plus 5 r plus 3 over r plus 2 r plus 1 whole square r, and we have x square here, so on. So this is a y in terms of r, and from here you can calculate y1 by just plugging the biggest root, that is 1. So first solution that is y1 is equal to y evaluated at r1 equal to 1. You should put r equal to 1 here. You will get a naught minus, put r equal to 1, this will be 4 and this will be 2, 2 will be cancelled, 4 by 1, I think this will become 4x, right? Okay, and this is also minus 4 a naught x, so that's fine. And you should put r equal to 1 here. You will get, I will do that calculation here, 6 4 over 3 2 square and 1 and 2 square, right? So 6 and 6 will be cancelled, 2 will be cancelled, I think 8 will be left with 8, so plus 8, right, x square and so on, right? And now this is the first solution, right? So in order to obtain the second solution, you should use that formula del y star over del r and evaluated at r equal to the least root, smallest root, that is 0, right? Where you should obtain your y star by multiplying r minus 0 with y, right? So I have to multiply this with r, so that will give you, that is y star equal to a naught x to the power r, and if you multiply the y with r, you have to multiply each and every term with r. So multiplying the terms of series with r will produce 2r plus 3 over r plus 1. This r will be cancelled in the denominator, plus 2 square r plus 5 r plus 3 and r plus 2 r plus 1 whole square x square. So this is a y star. Now I will differentiate this y star with respect to r. Therefore del y star over del r will be equal to a naught. You have to use that product rule, right? So that will produce the differential of first function will be x to the power r log x, and the series will be as it is, plus 2 square r plus 5 r plus 3 over r plus 2 r plus 1 whole square x square minus so on, right? And again the first term will be as it is, and the differentiation of the series, and again we have to rely on that formula using that log, right? So differentiation of this is 1, and for this I will use that shortcut formula. The function will be as it is outside, and inside bracket differentiation of it will give you 1 by r plus 3, right, and minus of 1 by r plus 1. Okay, so this is your x, here you have x, and for third term the function will be r square r plus 5 r plus 3 divided by r plus 2 r plus 1 whole square, and inside bracket this will become 0. Differential of this will be 1 over r plus 5 plus 1 over r plus 3 minus 1 over r plus 2 minus, see this power 2 is here, 2 over r plus 1, and then we have x square here minus so on, right? So this is the derivative, right? And now I will plug this my smallest root 0 here. Therefore y2 will be, you have to put 0 in this partial derivative, and plugging 0 here, that will produce a naught should be taken common, okay, and log x, and putting 0 0 6 by 2 3 minus 3, yeah, minus 3, putting 0 here, 5 3 2 1, 2 and 2 will be cancelled, so 5 3 15 to the 30, right, yeah, 30 plus 30 x square and so on, right? And for this term there is the second term, there is the second term, plus this will become x to the power 0 will become 1, so next series will be 1 minus, putting 0 here, 6, no, yeah, 6x, and then multiplied with this thing, and 1 by 3 minus 1, and that will produce minus 2 by 3. So multiplication of this with minus 2 by 3 will give you plus 4, right? Okay, and now the last term, putting r equal to 0 here, I have to do some rough calculation, and there is 2 square, 5 multiplied by 3, 2, right? This will be 1, fine. And inside bracket we have 1 over 5, or 1 over 3, minus 1 over 2, minus 2. So in all it will give you, this will be cancelled, 2 will be cancelled, 30 will appear outside, and for these two terms we'll have 15 as LCM, right? 5 plus 3, 8, minus 3 by 2, right? And on taking LCM it will give you 30, right? So that will produce 16 minus 15, say 45, yeah. So 16 minus 45 will produce 9 minus negative 30, 30 will be cancelled. The good thing is that, so 16 minus 45 will be the value, right? And that is how much? 29, minus of 29, right? So I am getting minus 29 as third coefficient, right? So I will write that minus 29. So minus 29 x square and so on, right? So this is the second solution, and the linear combination of these two solutions, y1 and y2, will be our second solution, right? So y is equal to c1 y1 plus c2 y2 is solution, right? Okay, so this is it for the Frobenius series method in case of when the root becomes infinite, right? So I will add a remark here. So this method works if the roots are distinct, first condition is that, and whether they differ by an integer or a non-integer, regardless of this point, they should be distinct, right? So this condition is sufficient if the roots are distinct, right? And obviously one is greater than the other, right? Then solution is always given by y is equal to c1 y1 plus c2 y2, where y1 is the solution obtained at the biggest root, and y2 is the solution obtained by this derivative r2, and y star equal to r minus r2 multiplied with y, right? So we can say that in general this method is applicable to all the cases when we get distinct roots, right? You need not actually focus on the behavior of the coefficient, that is immaterial. If you want to use this method, you can use this method freely for case 1, for case 3 and case 4, right? Regardless of the behavior of the coefficient, right? Because you can see in calculation that we actually did not use these coefficient. We need y in terms of r, right? So there is no point of taking these kind of coefficient, whether they are becoming infinity or they are becoming indeterminate. You just focus on the biggest coefficient and you obtain your first solution at that biggest solution, and then you obtain your second solution by this derivative formula, right? So that will give you complete solution, right? So again I am saying that this method works for case A, case 1, case 3 and case 4, right? So this is it for this Frobenius series solution. In the next video we will be taking some more on Frobenius series solution or its application maybe, right? So that will be the part of our next video. For this video, thanks.